Okay, welcome back to lecture number 10 on convex analysis. So it appears that these questions in the chat may probably not so helpful for following. So as long as there's not much activity in the chat going on, I thought, well, I should just start with the lecture anyways. Okay, so after we learned about the subgradient last lecture, so yesterday, let's move on and provide some more rules for subdifferential calculus and some properties of the subgradient, the subdifferential. So the topic of the lecture is subdifferential calculus, which is probably a little bit overblown because it's not that much calculus rules we're going to treat here. Okay, first we start with one result about for the properties of the subgradient. You already have seen that at each point the set of subgradient of a convex and lower semi-continuous function is bounded and closed. So here we have another property. If we have a proper and convex function, then it holds that the subdifferential is not empty. But not always, but it is not empty, and not empty, and it's also bounded as long as x is in the interior of the domain of f. So that is the important condition here. If you're in the interior of the domain, we can guarantee that the subdifferential is actually not empty, and moreover it is also always bounded in the interior of the domain. Now that's not the full truth. The full truth is that it's not empty if and only if x is in the relative interior, but we're not going to prove that here. This is enough for our purposes. Okay, let's go on and prove that. So, okay, let's first go for boundedness. That is more or less an immediate consequence of the fact that if a convex function is locally bounded, then it's locally Lipschitz at that point. So if you have x is in the interior of the domain of f, then f is locally Lipschitz at x0. This is proved at the lemma 6.1. So what does it mean? It means there exists a positive delta such that whenever x minus x0 is smaller than delta, then it holds that the images are no further apart than 1, for example. This is one way to prove, to show, or to write down local Lipschitz continuity. Okay, what does it mean now if we have if we had a subgradient, p and x, subgradient of x0, and then then we have for all x, we have that f of x 0 plus delta, not plus delta times x minus f of x0. This is larger or equal to p inner product of this with minus that, which is exactly delta x. So this is the subgradient inequality with the 2 points x0 where the subgradient is taken, and the other point is x0 plus delta times x. And if we also, so this is just a subgradient inequality, the difference here is larger than that. And if we also assume that the norm of x is bounded by 1, then the difference of these two arguments here is bounded by delta, which means that the difference of these two function values is bounded by 1. Okay. And this then shows that that the inner product of p with x is small equal 1 over delta. I don't know, probably you should do it like this with equality signs here. And since this holds for all x with norm smaller than 1, we can take the supremum over x, supremum over norm x small equals 1. P times x is still smaller than 1 over delta, but this here is actually nothing else than the 2 norm of p. And this is what we wanted to show. If you have a subgradient, then you have a uniform bound. That's it. So this is the bounded set. Okay, so that was the first part. Second part is existence. So if we have x or x0 in the interior of the domain, yeah, we assume. Oh, there's also the typo in there. Okay. So if we have this x0 in the interior of the domain, we also have that the interior of the epigraph is not empty. Why? Yeah, because this x delta, no, x0 is in the interior, so then we can just form something like a delta ball around x0, and then take the product with something like f of x0 to infinity, and this is then this open set is then contained in the interior. Probably we should add some constant here in the interior. It's totally contained in the epigraph of f. So this open set is contained in the interior, which means that the interior of the contained in the epigraph, which means that the interior of the epigraph is not empty. Also, we have that this pair x0 f of x0 that's not in the epigraph. Okay, it's just yeah, not in the interior, yeah, because it's on the boundary. It's not in the interior of the epigraph, and hence, since the epigraph is convex, we can separate this one here from the interior of the epigraph. So proposition 3.7, which was the proper separation theorem, says there exists a pair P0 T0, P0 T, RD times R, which is actually not the zero element, such that the inner product of P0 with X plus T times S is smaller than lambda whenever X is in the domain of F and S is larger or equal to f of x. This is just the condition. So this is the inner product of this tuple here with xs, and if this xs comes from the epigraph, which is just this, then this should be smaller, equal to lambda. And if we put this point in here, which means we take p0 times x0 plus t times f of x0, then it's larger or equal to lambda. So that's the separation of the epigraph from this point here. So picture looks like this. So if you have here our x0, then this is the x0, f of x0, and we can separate this point from the epigraph. So this lies on the one half plane, so boundary included, and this lies on the other half plane, boundary included. Okay, so this actually already looks like the picture that there should be the subgradient. The only thing which we don't know yet is the t. This may be 0, and if the t may be 0, it would be 0, then this separating hyperplane would be vertical, and then it would not correspond to a subgradient. So the only thing which is left to show is that t is non-zero. So we know the tuple is non-zero. And now we have to eliminate the possibility that t itself is 0. Okay, the first thing is we can take here every x in the domain and every s larger, so we can also take x equals x0 and not t, actually s equals f of x0. And this then these two things are the same, and we see that lambda actually has to be equal p0x plus p0x0 plus t times f of x0. Okay, we also know that t what I said previously was wrong. So we have to show that P is non-zero, and non-zero 0P would correspond to a vertical hyperplane. Sorry, the T doesn't play a role here. The P. Okay. So we conclude that T has to be a negative. So why? If T would be would be positive, then we could, because this holds for arbitrarily large S, we could just, so this would be a positive number, this is any number, then we could make the left-hand side as large as we like by making S as large as we need. So this would be, would contradict this here, because we can send S to infinity, so that's the first thing. And what about T equals to 0? If T would be equal to 0, then these things would not be there. We could flip the sign of one of the inequalities and add them together. This would show us that P of P0 in a product with x minus x0 would be non-positive by these two inequalities here. Flipping one of them and then adding up. And this would hold for all x which are at least at most delta close to x0. But it would hold in a full neighborhood, in an open neighborhood of x0, and then we see, well, products can't be, if they're all negative, but this vector can point in any direction here, that means this would imply that P0 would be 0. So they both would be 0 simultaneously, and this contradicts the known fact that this is not, the tuple is not 0, so they can't be 0 at the same time. So T is in fact negative, it's non-zero, and now what we do now is we set P equals to minus P0 divided by T, and this will be a subgradient. And this guy fulfills, we can probably get it from one of these inequalities here, that then f of x0 plus I think this one, this is the one we can transform, p times x minus x0 is smaller equal f of x for all x. And this shows that p is in fact a subgradient of f of x0. Lots of typos to the left. Okay. Good. That's that. So in effect, I was confused twice. The important thing is to show that T is non-zero, because if P and also negative. Because then we can do this construction here. And also note that at some point we have to divide these inequalities by T, and since T is negative, the sign changes. The direction of the inequality changes. So this is how we arrive at this thing here. Okay. Good. So the good thing is subgradients always exist, at least in the interior of the domain. They don't need to exist at the boundary of the domain. We saw that already. So if the function arrives at the finite number but infinitely steep, which may happen, like think of square roots, then subgradients need not to exist on the boundary. Okay, so what are subgradients good for? A lot of things. The first thing is they characterize optimality. They really characterize. So that's a very simple observation. Goes under the name Fermat. The same Fermat as from Fermat's last theorem, but this is much simpler here. This is already known from analysis from Calculus 1. If the gradient, or if a function has a minimum at some point, then the gradient has to vanish, in the case of differentiability. In the case of convexity, the situation is a little bit nicer, actually, because local minima are also global. So we can even calculate global optimality by differential methods. So what we need is f from Rd to R proper and convex. And then we have x hat, the global minimizer of f, if and only if 0 is an element of the subgradient of f at x hat. It's really an if and only if. In the differentiable case, you only have this direction here, but then you know that 0 has to be the gradient of f at x hat. Because of convexity, you have both directions. Yeah, that's it. And the proof is very simple. It's really nothing, not much is in there. If this is the global minimizer, then we know that f of x is larger or equal to f of x hat, and for all x. And it's so simple, so we can just add this here. We just added 0, and this shows that 0 is in the subgradient of f of x hat. That's just it. So since f of x is larger than f of x hat, we know that the subgradient, which is the element that any subgradient, know that everything we can put here is a subgradient. We can put 0 here because then this just vanishes, and so 0 has to be a subgradient. And the other way around is kind of the same. So if 0 is in the subgradient, then this holds for all x. This is 0, so this is also if and only if, and that's already it. So if 0 is a subgradient, this holds for all x. This shows that f of x is larger than f of x hat for all x, so x hat is the global minimum. It's really very, very simple. Okay. Okay, a few more examples of subgradients. And again, a good example is always indicator functions. So C, convex and non-empty. Yeah, let's do it just like this. So and then what is the subgradient of the indicator function of C at some point x0? Okay, one thing is clear, it's just not there, it's empty if x0 is not in C. This is just by definition, because an indicator is plus infinity, and in this case there's just no subgradient at all. So, and if what happens here, if what is the subgradient inequality now? So this is the second case, is just x0 is in C, and let's write down the subgradient inequality in this case. So you need that this is larger or equal this plus p times x minus x0. So, but since we are now in the set C, this guy is actually 0. So what are now the interesting cases? So this has to hold for all x, and if x is not in C, this is in plus infinity anyway, so it's always fulfilled no matter what p is. So then only interesting things occur if x is in C, but then this is also 0. So, and there we have it. This is the set of all p such that for all x, oh, there's also an inequality sign missing. We have that the inner product of p with x minus x0 is non-positive. It just comes from here. Okay. So, and then there's more. So if now is x0 is in the interior of the set, then again you can choose the axis in the full open neighborhood of x0. This points in all direction, which means that p has to be 0. So in the interior, the subgradient just consists of 0, which makes sense because if it's in the interior, you can the only hyperplane which fits below is the 0 hyperplane. Okay, then so outside of C it's trivial, inside of C it's also simple. The only thing, so in the interior of C it's also simple. So the only interesting things are what is at the boundary, what happens there. And then just have to look at this inequality here, and we can remember from, I don't know which lecture it was, but it has a geometric meaning. So let's see that this is our set C here, and you take a point x0 here at the boundary. What does that mean? It means that the angle of the subgradient P and all of these guys, which points towards a point into the interior of C, or into C. This angle has to be larger, equal to 90 degrees. So, and this, we have seen this before. This is exactly, so all these vectors here are subgradients, and this is exactly the normal cone at the point x0. So at this point here, we have this right angle here and this right angle here. So this here is the subgradient. This is our x0. So the subgradient of the indicator function is exactly the normal cone. Okay, that's very nice. And in fact, it holds at all places. Also outside it doesn't make sense, but even inside the normal cone is just 0. Okay, so this was the simple facts about subgradients. Set of the subgradients exists, at least in the interior. Set of subgradients is bounded, closed, and convex. That's all nice. Subgradients can characterize optimality, global optimality of convex functions. So, but now comes the catch, two things that not always hold. So, Theorem 10.4. So, if we have two convex functions, then we have that the subgradient of f of x plus subgradient of g at x is how it is related to the subgradient of f plus g at x. And the norm for normal differentiable functions, that's the most simple thing to prove. These things are equal for gradients and differentiable functions, but for subgradients it's just like this. It's just an inclusion. And there's nothing more you can prove, except you know more. So under these assumptions, nothing else than this can be proven. So it can be equal. So, and then when does it hold? So equality holds if, and it's not an if and only if, it's just an if. This is now very, very strange. There exists a vector point x bar, which is in the interior of f and g simultaneously, such that f is continuous at x bar. Okay, and I forgot one thing. Let's start again. So f and g are convex and proper, and then what I forgot to say is for all x, this inclusion holds, and you have equality for all x if there's some point unrelated to this x, totally unrelated, where both functions are simultaneously finite, and f is one of the two functions is continuous at this arbitrary point. This looks totally strange to me, so you will see examples why this is important, and the proof also reveals a little bit about this. So, but you have this inequality always, and you always have equality, always, if there's just one single point, both of them are finite, and only one of them is continuous at the point. So that is the sum rule, the subgradient sum rule. This inclusion always holds. Equality, you need something more. And this is just an if. It's by no means an if and only if. There are tons of other conditions which may be applied to guarantee equality of subgradients. So the second thing is, it also can go wrong if just one function is proper and convex, and you have D times n matrix, and then you can form a new convex function, which is now defined on Rn, by just defining that f of ax, this satisfies, and for the gradient you would know what happened. If f is differentiable, then the gradient of phi would be a transpose times f ax. That's the ordinary chain rule. So of course, the chain rule for derivatives says the inner derivative goes to the right, so the a goes to the right, but the gradient is the transpose derivative, so you have a transpose to the left. But here it holds that a transpose subgradient of f of ax is just subset of the subgradient of phi at x. Again, no equality in general here. For all x again. And what about equality? Equality holds if there exists again an unrelated point x bar such that f is continuous at x bar and what? Sorry, it's continuous and finite at ax bar, of course, at the image point. So this is the sum and one of these chain rules. So there's not many chain rules available because in general you just can't concatenate convex functions. So of course, just by domain and image space do not match, and even if they do, d equals 1, sometimes it's just concatenation of convex is not necessarily convex. So there's not much you can do to precompose a convex function with linear works, and nothing else in general works. So for linear, even then, it's complicated. So that's the thing. We will have a proof in a few seconds. So maybe, so actually the proof takes the rest of the lecture. So I can't, I have to postpone the counterexamples to next lecture. So there were I wanted to show you examples where this inclusion is strict and this inclusion is also strict. So these are important to keep in mind. Okay, so now let's come to the proof. Okay, so the inclusions are in both cases not that hard. So the inclusion would be, so if we have, so that's what we wanted to prove. We wanted to prove that subgradient plus subgradient is contained in subgradient of the sum. That's what we want to prove. And so we start with something on the left-hand side and show that it's in the right-hand side. So if P is in the sum of the subgradients, and here, since we are new to the business, remember these are just two sets, that's the Minkowski sum, which means that P can be written as Q plus R, with P is in the, not P, but Q is in the one set, subgradient of F at X, and R is in the subgradient of G at X. So what we do now is we write down both subgradient inequalities, which say for all y, we have that f of y is larger than f of x plus this subgradient q times y minus x, and for g we have g of y larger equals g of x plus r times x minus y. Adding them up gives what we want, f of, so for all y it holds f of y plus g of y larger f of x plus g of x plus q plus r y minus x. And this shows that q plus r is in fact in the subgradient of the sum. So it's simple. So we this shows that there are individual subgradients in each. They both fall for the subgradient inequalities, and then you can just add the subgradient inequality and arrive here. So the other way around, you see it's tricky. It's not straightforward because this does not work the other direction. So what you in the other way, we assume that we have a subgradient of the sum, which means we have these inequalities for just one vector here, and then it's totally non-obvious how to split up this vector into two parts, such that one of them works for this for this subgradient inequality, and the other works for that subgradient inequality. So it's totally non-obvious at least to me. I have, it's just not simple. But this shows the inclusion. So this is now done. Okay, so what now for equality? So we assume that there's this x bar, which is in both domains. Okay, and remains. So we know the inclusion always holds. It remains to show that the subgradient of the sum at some x is contained in the sum of the subgradients. Okay, so if not either, so if f of x is infinity or g of x is infinity, then this is clear, because then the left hand side is also then f plus g is infinity and the left side is empty. Also then f plus g at x is infinity, hence the subgradient of f plus g is empty at x. Nothing is to prove. Also the right side is also empty, but then it still holds. Okay, so we don't need to assume this case that one of them is infinity, so we only need to consider the case both are finite, which means we have x is in the intersection of the domains. Okay. So now the goal is that we want to, so if we have a subgradient p of the sum, and our goal is to decompose it into q plus r, such that q works for f and r works for g. That is what we want to show. Okay, so I don't write that down. So we want to decompose p into q plus r, and q is a subgradient for f and r is a subgradient for g. So what we have is that f of y plus g of y is larger or equal to f of x plus g of x plus p times y minus x, and we have that for all y. That's what we have. So we rewrite this a little bit different. So we separate the contributions of p of f and g in the way that there's f of y minus f of x, and then we put this all to the left hand side, minus p times x minus y is larger than g of x minus g of y. So we call the left hand side capital F of y, because x is fixed, and the right hand side will be denoted by g of x. And note that f is again convex, because this is convex and we subtract the constant and the linear function, and the g is concave, because it's basically minus g shifted. Okay, so what we now do is, so the tool we're going to use is separation of convex sets, because separation is our tool which kind of guarantees the existence of certain hyperplanes. We can guarantee this by separation arguments. And we're going to need hyperplanes, because hyperplanes will be gradients or subgradients. So this is the tool we're going to employ. So, and for separation we need convex sets. And the sets we're going to construct, the set C1 will be the set of all tuples y alpha in Rd times R, such that alpha is larger or equal to f of y. Okay, and the set C2 will be the set of all tuples y alpha in Rd times R, such that g of alpha is larger equals g of y is larger equal to alpha. Okay, so one thing is we could restrict the things a little bit, so we don't need to consider the full Rd here. It's enough if we put here the domain of f, because otherwise this is plus infinity anyways. It's also enough to put in here the domain of small g of that guy here, because otherwise it would be negative infinity and so on. Yeah. So this is enough here. So these are convex. Both of them are convex sets, because this is kind of the epigraph of F, and this is kind of the it's how it's called, the subgraph of G, and G is concave, and so the function, the set of tuples which are below the graph, it's the convex function again. So this is an epigraph, and this is kind of a flipped epigraph. So still convex, and moreover, and non-empty. Why? Yeah, you can just put in. Just know that f of x and g of x is 0. So if you put in, so you can just put in x and 0. X and 0, then this works and this works too. So they both are non-empty. And moreover, now the important thing is here by this implies that C1 and C2 only share boundary points. So they only intersect, only intersect at the boundary, because this f of x is always larger or equal to f of, this has to be g. G of y. Okay, so then it's clear that it's so if you write in x, you have to be confused for the last minutes. Yeah, so g of y is small g of x minus the small g of y, so this is the reason why g is concave, and this explains why this set here is convex. So, and by this inequality, this is always larger or equal than that, so they only can intersect at the boundaries. Okay, so, and now comes the big tool we're going to use. We can separate two sets which only share boundary points by hyperplanes. That is the proper separation theorem. Theorem 3.9 was the proper separation theorem. There exists Q and A non-zero such that for all x y1 alpha 1 in C1 and y2 alpha 2 in C2, it holds that the inner product of this with that or is larger than this with that. And I just write it once like this. So I wanted to have this on the left hand side, y2 alpha 2 with qa smaller equal to y1 alpha 1 qa, and put differently, it's y2 times q plus alpha 2a, and this is y1 q plus alpha 1a. Okay, now comes construction we've done before. We want to show that this a is now in this case actually positive. Okay. So why does that follow? So one thing is in C1 we can find the point x alpha 1 is in C1 if alpha 1 is positive. You see that here, you see there. If we take y equals x, then f of x is 0, and so we need alpha to be positive. And x alpha 2 is in C2 if alpha 2 is non-positive. Okay, so you plug both points in here. Then these guys are the same, and we get the inequalities that alpha 2a is smaller equal to alpha 1a, and This is positive, this is negative, so alpha a has to be larger equals to 0. So if a would be negative, this cannot hold. These will contradict. So we already know that. But what about alpha equal to 0? So what if alpha would be equal to 0? Then what would we have? We would have, in this inequality here, we would have y2 times q would be smaller than y1 times q for all y1 in the domain of small f and y2 in the domain of small g. And also this is one thing, and also we would have that x bar, the one point which should exist actually, times q is smaller equal y1 times q for y1 in the domain of f. Okay, but now since this y bar, so f is continuous at y bar, which means that the y bar has to be in the interior. So in all directions, f bar remains finite. So we can just you can move x bar into all directions and still get a finite point. So we can plug in here for y all points in the domain of f. X bar is in the domain, but x bar is also in the interior of the domain. So we can move around the point x bar a little bit. So since f is continuous at x bar, it holds that x bar plus delta x is still in the domain of f for delta x small enough, but nothing else, so probably just in some delta ball or something. And then these two things, so you can put in here x bar plus delta x. But this then shows that q is smaller or equal to delta x. And you could use plus minus delta x actually to make this next argument a little bit simpler. And so this would then imply that q would be 0, and this would be the contradiction that the tuple q alpha is not 0. So again, this is the argument, and this is where this comes in, that we need the point of continuity. So we see we don't need a point of continuity, we only need something that from this inequality here, we can conclude that the q has to be 0. And what is enough is that we can choose y1 into enough directions, so as x bar plus enough directions to conclude that the q has to be 0. Okay, so a can't be non-negative, it can't be 0, so it has so it can't be negative, it can't be 0, so it has to be positive. So hence a really is positive. Okay, good. So how do we conclude now? Since a is now positive, you see here in this that you could also, without loss of generality, assume that a is equal to 1. You can just scale up and down so that everything still works. So without loss of generality, assume that a equals 1, because everything can be scaled. And yep. So how do you proceed? Now we need to construct the subgradients, and this is not that far away anymore. So we have that these tuples f and capital F, y and capital F of y is in C1, y and capital G of y is in C2. Whenever y is in the domain of f or in the domain of G respectively. So in the first case this holds, in the second case this holds. Okay, and this is just saying that Q times Y plus f of y is larger equals to B. And Q times Y plus G of Y is smaller equals to B, coming from this up here for some B. Okay, it still remains a little bit open what this B exactly is, but we'll see. So because we can take y equal to this one x, which is in both of them, which is in the domain of f intersected with the domain of G. If we take that, then you see these guys here. Then f and g, f of x is equal to g of x, both are 0, and in fact you see that the b has to be q times y. And y is x, so q times x. Okay, so and what do we get? So this b is q times x, and this shows us that for all y in the domain of f, it holds that f of y minus f of x. So I just express capital F and small f minus p times y minus x plus q times y is larger equal b, and the b have been seen as q times x. So on this inequality is the same as, so you bring these to the left hand side, so now you bring all these things to the right hand side and see f of y larger equal f of x plus, and then we get here, if this goes there, we get q times x minus y, flip the sign, you get p minus q x minus y, like that. Okay, and then this shows, again for all y, this shows that p minus q is a subgradient of f. And this is what we wanted to do, right? We started with p is subgradient of the sum function, and we wanted to decompose it into two. The q we got from the separating hyperplane, and it has the property that if you subtract the q from the p, we get a subgradient of f, and similarly, from this inequality here, we get that q itself is in the subgradient of g of x. Whew. And this proves the claim. This proves the first claim. Okay. One can also paint a picture, but probably so the picture goes roughly like this. So if we, so the epigraph of f maybe looks like this, and so now it's difficult if I write down, if I show you g and then try to sketch f plus g, the picture gets a bit messy, but we may just consider these two sets, c1 and c2. So because, well, we have here also a little bit things shifted around, but the picture is roughly like this. The set c1 is kind of like this. Actually, it's a little bit tilted because we subtracted the subgradient, but let's leave it like this, and it's also shifted by constants, but the picture that this set C2, so let's not write f and t, but so the set C1 and C2, they look like this, and they actually touch here at least one point. So this is how we construct the set C1 and C2, and they're related to the epigraphs of f. So this is a shifted and slightly tilted epigraph of f, and this is also the flipped and shifted epigraph of g. And then this is the separating hyperplane we're going to use, and the slope is q of this hyperplane. And if you look at this here, the shift of the C2 amount comes from the epigraph of f by tilting it with p, and then you can probably imagine that p minus q is then, so I think this here tilts to the left, and p minus q is then a subgradient of f itself. And it probably can also see that q should be a subgradient of the function g, because it's this negative epigraph here. So kind of. So this is the trick, that you can kind of transform the problem into the problem of finding a hyperplane which separates C1 and C2. This also shows you how to generalize this results into further situations, so you probably don't have this assumption. Okay, and so one thing where this doesn't work is the case where this graph of C1 looks like this. It gets infinitely steep here at the point, and this set here is the same, so you come here vertically and then go like this. So, and in the case that C1 looks like this and C2 looks like this, it's still the same thing, kind of so convex concave, or epigraph of convex, subgraph of concave, and they still touch only in boundary points, but the only separating hyperplane here would be vertical. That's then a problem. And this is how you construct counterexamples. So vertical hyperplanes do not help you anything. They do not allow you to split up the subgradient. Okay, so that was the first part, and the second part is kind of equally long. It's a little bit shorter. So again, first show the inclusion. So what do you want to show here? The inclusion which we wanted to show is something like A transpose subgradient of f of ax is subgradient of f precomposed f. That's what you want to show in the second part. And so the inclusion, first the inclusion. Okay, so then let an element in the left hand side would be of the form A transpose P. We call that Q, with P is in the subgradient of f at the point AX. And so now notation is important. So this should be the subgradient of the concatenated function, and this is the subgradient of only f but evaluated at the point AX. It's something totally different right here, actually. Okay. So what does that mean? And this here is what we call phi. So just using this subgradient inequality here, this gives us now for all y we have, so we start with phi of x plus q times y minus x, and you want to show, our goal is to show that this is always larger equal to phi of small equal phi of y. If you can manage that, we've shown that q is a subgradient of, so if you can fill in the blank here, you can conclude that q is indeed a subgradient of phi at x, and this is what you want to show. Okay, so just plug in what is phi. Phi is f of ax, and what is q? Q is A transpose P. This is y minus x. Okay, and now it's pretty simple. We keep this as is and just use the property that the transpose can move over to the other side of the inner product, and gives us an ay minus ax. So, and now we can use that P is a subgradient of f. So this is the subgradient of f at exactly this point. So this is smaller equals to f of ay for all y. And this is exactly y of y. So that's the inclusion. That's actually very simple. So this is the same proof as for the chain rule for differentiable functions. Okay, so now again let's check why the equality is difficult. So for the equality, you assume that you have a q in the subgradient of phi at x, and write down what that means. It means for all y, you have that phi of x plus q y minus x small equals phi of y, and this is the same as saying f of ax plus q times y minus x smaller equals f of ay. And so the goal is to show that this Q can be written as something like this. So you would like to introduce an A here, but you can't. Yeah, I think if A would be orthonormal, you could just plug in here an A transpose A, because this would be the identity, or an A transpose, and then everything works out. But this is not what we can do here. It doesn't help us. Okay, I would plug in an A transpose A here or something. Okay. Anyways, you want to write this as A transpose Q, and it's not clear how to do that. So again, we need to kind of squeeze an additional separating hyperplane, and this now goes a little bit different. Our set C1, which we're going to use, is this just the epigraph of F, and the set C2 is a little bit more complicated. It's the set of pairs AY here, and then here we use F of AX plus QY minus X. This is for that, for all Y in RD. So now we again use that epigraph of F is non-zero. The interior even, because this F has the property that F is continuous at some point AX bar. So the interior of the epigraph is not empty, which is exactly the interior of C1 now. And also yeah, this is not what I wanted to write. And also, again, these two things only intersect at the boundary. So we can separate C1 and C2. Again, Theorem 3.9 is what we're going to use. There is a vector, the tuple, which is non-zero, and this is now denoted by Q0 and alpha 0, such that this vector separates these two sets. And what does that mean? It means that Q0 times Y bar, as I call it here, plus alpha 0 times A. No, I think it's an alpha what I want to use, times alpha is smaller equal to lambda for Y in the domain of F, and alpha larger equal to F of Y. Y bar and Y bar. This is separation. So this lies on the one part of the side of the hyperplane, and the other goes. So we have to test with these guys here. So it says that Q0 times A Y plus alpha 0 times this here, F of AX plus Q inner product Y minus X. This is then larger equal lambda for all the Y in RD. So this is now the separating hyperplane for these two sets. Okay. So and again, alpha 0 can't be positive, because then you could make the left-hand side here arbitrarily large by sending alpha to 0. So giving this guy here star, so you can set alpha to infinity in star, and this can't be because the right hand side is bounded. And alpha equals 0 can also work, can also not be, because, and this is now again a little bit like before, the continuity of F is what it destroys. So if alpha 0 equals 0, then you would have that Q times Y bar would be smaller equal Q0 times AY for all y bar in the domain of f. So it just comes from here. If this alpha 0 is 0, then this vanishes, and so this is smaller than lambda, this is larger than lambda, so we have that, and we can do that for all y bar in the domain of f. Okay, and again, we could, so this part of this parenthesis here, we could choose y as x plus minus delta x again, which then gives that, and y bar as a of x plus minus delta x. This would work, and this would all stay in the domain of f, and this would show us that q0 has to be 0 like before, and this is again not possible because they both can't be 0 simultaneously. Okay, so we know, so hence alpha 0 is again negative. Okay, now it's almost done. We set y bar as ax and alpha as f of y bar and y as x, and we get here from these things here that then lambda has to be equal to q0 times ax plus alpha 0 times f of ax. So it comes from here. If we set all these, we observe that this is the only possibility for lambda. Okay, this now this gets 2 stars here, and we say now using this in 2 star in the second inequality here, we get that q0 times ax minus ax q0 times ay, sorry, minus ax plus alpha 0 times q y minus x is larger equal 0 for all y in Rd. Yeah, this is also, this is a q, this is a q0, so yeah, that's correct. Yeah, and then this shows us, so we can just kind of yeah, we can move the a over here with an a transpose, and then kind of, because then y minus x can be basically any vector, we still can conclude that the left hand side has to be 0, what's in the left hand side of the inner product, and this says as well the q has to be minus 1 over alpha 0 a transpose q0. And if we now set p equal to this 1 over alpha 0 q0, we get from the first inequality that for all z in the domain of f, it holds from the first, yes, kind of from the first, that p times z minus ax plus f of ax is then smaller equal f of z. Remember that alpha 0 is negative, hence you have to flip the sign if you divide by that. And this shows that the p, so this p here is actually in the subgradient of f of ax, and hence we've shown that the subgradient of phi of x is contained in a transpose subgradient of f at ax. And this is what we wanted to show. Okay, I find these proofs are kind of exhausting. So they are. So the concept is not always totally clear, and it's not so simple to make very clear. So you have to transform the problem of finding the right kind of subgradient which you need to finish the argument into a separation problem. And then after you can just have separated, you need to ensure that the separating hyperplane is not vertical. And in this case, you also need to figure out the correct sign of the alpha, and so that you end up with the right thing down here. Is because to end up here, you have to divide by alpha 0 at some point, and so to figure this out is not totally straightforward. Okay, that was a lot of stuff. There's also no break, because why should there a break? If you only watch this remotely, you can just take the break whenever you like. If you watch it asynchronously, so I don't need any breaks as long as it stays like that. Okay, great. I hope I didn't introduce too many mistakes. I only found 1, 2, 3, 4, 5 errors in my lecture notes, which I'm going to correct, and I'm damn sure that there are more errors, and I would really happy if you submit more errors in the forum of the lecture, so that I don't have to catch all the errors by myself. Okay, thanks for watching, and see you on